Now let's do a worked example of all this electrostatic stuff. I'm going to ask, could we use static electricity to make a flying car? As you'll rapidly learn, I'm a bit obsessed with flying cars. They'd be so cool. Can we actually get a flying car? Well, here's one of my possible ideas. We have the ground, and maybe this is the road and have some metal plates in it at various places connected to some voltage supply. And then we have our flying car, like something out of Star Wars. And we put a charge on the bottom of the flying car. I'm saying positive, but it might be negative. Doesn't matter. As long as we have the same charge on the ground. So we might apply the voltage to whichever metal plates are underneath the car, so they have the same charge on it. So you get like charges repelling, and that keeps your car hovering in the air. So what do you reckon? Does that sound cool? Well, this is a probably crazy idea, so let's do some ninja physics and try and work out very quickly and very dirtily if it's roughly even sensible or if it's totally stupid and not worth doing a more detailed calculation. So we're going to do the roughest calculation we possibly can with the aim of finding out very quickly if this is totally stupid or not, because most ideas are totally stupid. So, some numbers first. What's the weight of a car? That's typically 1 to 2,000 kilograms. I call it 1,000 kilograms to make it simple. And how high do we want it to hover? Let's say about 10 centimeters, because that's enough to go over any bumps in the road. Yeah, a meter would be better, but it's probably going to be harder. If it was only 1 centimeter, then your one pebble on the ground is going to do nasty things to the bottom of your flying car. So 10 centimeters sounds ballpark okay. And of course, if our initial assumptions turn out to be totally wrong, we can go back and revisit them. Maybe we even make the whole car out of carbon fibers and make it lighter, or maybe we need to go higher or lower. But that's a good starting point. Okay, so how do we actually approach this? Well, we need the car to stay hovering, and its weight is trying to pull it down, so we need an upward force that's going to balance that. So there's going to be a force balance. We're going to have some charge Q here, and I assume there's equal opposite charge on the ground. And so we're going to have to produce an electric field from the charge on the ground, E, and E times Q is going to be the upward force, and that's got to be equal to the weight of the car times G. Okay. Now, working out the electric field from sheets of charge is something we'll do later in the course, but it's complicated. So let's approximate the car as a point charge and the ground as a point charge directly underneath it. That's going to be a bit different from the actual distributed charge, but probably not very different. So it'll give us probably to a factor of 2 the right answer, and it'll be a lot easier because we can just use Coulomb's law here. What that's telling us is the force is going to be given by Coulomb's law. So that's 1 over 4 pi epsilon naught, charge of 1 times charge of 2, over the distance between them, let's call that r, squared. Actually, let's call it d for distance. It doesn't really matter as long as you're consistent. Okay. So that's our equation, mg equals 1 over 4 pi epsilon naught q squared over d squared. That tells us what we need to do to stay in the air. And checking it, you will always make mistakes, so it's always worth checking. That's just Coulomb's law equals weight, so that's too simple to bother checking. Now you notice that rather than write down d as 10 centimeters or m as 1,000 kilograms, I've actually named them with symbols. So I call it m, and m equals 1,000, and I've called it d, and d equals 10. It's always better to leave things in the form of symbols as long as you can. The reason for this is, first of all, it's a lot easier to check, and secondly, if you need to reuse the calculation, let's say you want to try a different mass or a different distance, it's totally trivial if you do it just by changing the symbol at the end, what it's worth, whereas if you put numbers in at the beginning, it makes it much harder. So general rule of, in fact, all physics, invent symbols and use them. Don't plug the numbers in too soon. I know it's very tempting because most of us are much better at arithmetic than we are at algebra, but no. If you're working out something, give it a symbol, do the algebra, and only put the numbers in at the end. Okay, so let's find out how much charge we need here. Let's rearrange that. So let's see, we're going to get q squared equals 4 pi epsilon naught mg d squared. So that's just taking all the bottom there up to the top over there. So q is going to be the square root of that. Check that for plausibility. If d goes up, so you want to fly higher, you're going to need more charge, which sounds plausible. If the car is heavier, you're going to need more charge, which sounds plausible. So this looks vaguely plausible. If it was a 1 over m or a 1 over d squared, that would be a problem. Limiting cases, if the mass is 0, you need no charge, which sounds sensible. If it was like e to the m, then you'd need charge to support 0 weight, which would be ridiculous. So the checks are looking good. Okay, let's put some numbers in. We know our numbers from up here. I like to do this using Python, a Jupyter notebook. So let's have a look at that. Here we go. So I've imported maths. I've set up my variables. And then I type the equation in Python syntax and print. And I hit Shift Enter for that key, and it tells me the answer. So we need a charge of about 10 to the minus 4 coulombs. Now, if you're like me, you probably don't actually know quite what a coulomb is, so that sounds small and maybe reasonable. But is it? What we can actually do is try and work out the electric field, or the voltage. Now, the voltage is going to be roughly the electric field times the distance. Electric field is just given by Coulomb's law, but with one of the charges taken out. So it's q over 4 pi epsilon naught d squared. So we know everything else here, 10 to the minus 4, we know d, so we can pick that in the Jupyter notebook and plug some numbers. I've already done it down here. And we get an electric field of this, which is about 100 million volts. Whoops. So that's not looking so plausible. I should mention that the voltage, if you remember, the potential difference is just the electric field times the distance. So delta voltage is just this times the distance, which is what the equation I just showed you. About 10 million volts. So that's not feasible. What's actually going to happen is that's way above the breakdown voltage of 3 million volts per meter, the breakdown electric field, so you're going to get immediately lightning bolts between here, or lightning bolts out into the air, and the whole thing's going to collapse and burn and explode. Bummer. I don't think this is going to work. Oh well, it might work in a vacuum, but if you've got air, it's way above, these voltages are much too high, you're going to get discharge and it's going to crash and burn. Ah well.